welcome. Think about the water you drink every day. Where did it really come from? We tend to assume it's, from Earth, part of the package. But what if it's older, like much older? Today we're diving into some fascinating new research that suggests the water on Earth isn't just terrestrial, it might actually be cosmic.
That's right. We're talking about water that potentially predates our own sun.
So our mission today is to follow the clues, a kind of chemical fingerprint, really, to trace water's origins back through time. Is it from here or from the stars?
And the story has recently taken a dramatic turn thanks to observations from the Atacama Large Millimeter Submillimeter Array, ALMA. It gives us this incredible window into the chemistry of space.
Right, ALMA. And it was looking at a young star, V83 Orionis.
Exactly. A star, much like our sun when it was young, surrounded by a disk of gas and dust, basically a planetary construction zone.
And in that disk, they found water. But not just any water.
No, this was the key. They detected something called doubly deuterated water, D-Euro, sometimes called heavy water.
D-Euro, okay. Why is that specific molecule so important?
Well, finding DO there is what the researchers called the smoking gun. It's direct proof that the water in that disk, and by extension, the water that will eventually end up in its planets and comets, must be older than the star itself.
Older than the star.
Yes. It means the water wasn't made in the hot environment right around the young star. It was inherited. It's pristine material from the cold, dark, interstellar cloud that the star formed for millions of years earlier.
Wow. So cosmic hand-me-downs, essentially. Frozen molecules delivered intact. But let's unpack that fingerprint for the listener. What's deuterium and why is it the key here?
Okay, so deuterium, symbol D, is basically just a heavy version of hydrogen, H. It has an extra neutron in its nucleus. Doesn't change the chemistry much, but it changes the mass.
And the ratio of D to H, that's the fingerprint.
Exactly. The DH ratio tells us about the water's history, because the process that stuffs extra deuterium into water molecules, enriching it, only really happens efficiently under very specific conditions.
Which are?
Extreme cold. We call it cold chemistry. Think deep space. Inside those vast interstellar clouds where stars are born, temperature's just a tiny bit above absolute zero, maybe 10, 20 Kelvin.
So barely moving? Freezing doesn't even cover it?
Pretty much. And in that environment, chemical reactions are slow, they're sluggish. And for reasons related to quantum mechanics and energy levels, it's slightly easier for the heavier deuterium atom to get incorporated into water ice compared to regular hydrogen.
So finding water that's loaded with deuterium means it must have formed in one of those interstellar deep freezers.
Precisely. You can't easily make highly deuterated water in warmer places like the inner part of a forming solar system.
Okay, so what's Earth's ratio? What's the benchmark?
Right. Here on Earth, our oceans have a DH ratio of about 1.56 times 10 to the minus 4. So about 156 deuterium atoms for every million hydrogen atoms, roughly speaking.
And how does that compare to, say, the raw hydrogen gas our solar system started with?
That's the interesting part. The hydrogen gas in the Presolar nebula, before planets formed, had a much lower ratio, around 2 times 10 to the minus 5.
Whoa. Okay, so Earth's water has, nearly 8 times more deuterium than the starting gas?
Exactly. That difference tells us immediately that Earth's water, or at least the building blocks of it, must have gone through that cold interstellar enrichment phase before being incorporated into the planet.
And the V883 Orionis detection fits this perfectly.
It does. The amount of DRO they found aligns beautifully with what models predict for this cold interstellar chemistry. It shows that the ancient ice from the cloud can actually survive the star formation process and get passed down to the protoplanetary disk. It's the missing link connecting the clouds, the disk, comets, planets.
And ultimately the water in our taps. Amazing.
It really is. Connects the cosmos right to your kitchen sink.
Okay, so we've established when the water likely formed before the sun, ancient ice. But now, how did it actually get here? How was it delivered to Earth?
For a long time, the leading theory was asteroids, right? Yes, the asteroid hypothesis held sway for decades, and for good reason. The chemistry matched up incredibly well.
Oh, awesome.
Well, certain types of meteorites, called carbonaceous chondrites, which are basically fragments of asteroids, have a DH ratio very, very close to Earth's oceans. That was compelling evidence.
Okay.
Plus, we know the asteroid belt contains a lot of water. Objects like Ceres, the largest asteroid, are thought to be maybe 17 to 27% water by mass. It's not liquid water, mind you. It's locked up chemically in clay minerals.
Right. And the thinking was that early Earth formed hot and dry, too close to the sun for water ice to survive.
That's the standard model. Earth formed in the inner solar system inside the snow line where it was too warm. So any water it might have had initially would have boiled off and needed water delivered from further out.
From the colder regions.
Exactly. From the outer asteroid belt, beyond about 2.5 times the Earth-Sun distance. Computer simulations show that during the later stages of planet formation, maybe tens of millions of years after Earth started forming, gravitational nudges from giant planets like Jupiter would scatter large, water-rich bodies, planetary embryos, inward.
And some of these slammed into the early Earth.
That's the idea. These late impacts delivered a significant amount of water. It's seen as sort of a natural consequence of how planets form.
But hang on, if Earth was still pretty hot from its formation, wouldn't these impacts just vaporize the water and blast it back into space? How did it stick?
That's a really good question. Two key things. First, the delivery was late, when Earth had cooled down somewhat from its initial molten state. Second, the water wasn't arriving as ice or liquid, but locked inside those clay minerals in the asteroids.
So it's chemically bound, harder to release.
Right. It takes more energy to break those chemical bonds and release the water compared to just vaporizing ice. This allowed Earth to hold on to the water more effectively, even with energetic impacts. Geochemical models suggest maybe 15% of Earth's building blocks came from this kind of chondritic material, which fits nicely with delivering the amount of water we see.
Okay, that sounds pretty convincing. Asteroids delivering water locked in minerals late in the game. Case closed.
Well, it seemed that way for a long time, but then comets made a comeback.
Yes, the comets. They were sort of ruled out for a while, weren't they? Because their water didn't match.
Exactly. It was a real puzzle. For years, measurements of comets, especially the ones coming from the really distant Oort cloud, showed DH ratios that were way too high, sometimes double or even triple the ratio in Earth's oceans.
Like Comet 67P, the one the Rosetta mission visited. I remember that being seen as like the nail in the coffin for the comet theory.
It certainly felt like it at the time. 67P's water had about 3 times the deuterium enrichment of Earth's. The conclusion was stark. Oort cloud comets, which people thought represented most comets, simply couldn't be the source of Earth's water. The numbers didn't add up.
So a whole theory kind of went on hold based on that.
Pretty much. But then new data started trickling in, challenging that view.
Okay, what changed?
The first hint came in 2010. The Herschel Space Observatory looked at a different type of comet, 103 Hartley 2, which is a Jupiter family comet originating from the closer Kuiper belt, not the Oort cloud.
Yeah.
And its DH ratio was surprisingly Earth-like, very close to our ocean water. Suddenly it wasn't so simple. Maybe not all comets are the same.
One comet isn't a trend, though. Did people buy it straight away?
Not entirely. It was intriguing, but skepticism remained. They needed more evidence confirmation. And that arrived in 2018 with SOFIA, the Stratospheric Observatory for Infrared Astronomy.
The airborne telescope. What did SOFIA find?
SOFIA observed another Jupiter family comet, 46P Virtanen, as it made a close pass by Earth. And the results were unambiguous. Virtanen's water was ocean-like. Its DH ratio was essentially identical to Earth's.
Wow. Okay, so now we have 2 comets matching Earth's water. That definitely complicates the asteroids-only picture.
It really did. It forced a major rethink.
But what explained the difference? Why did 67P have such high deuterium, while Hartley 2 and Virtanen looked like Earth? Was it just Oort cloud versus Kuiper belt origins?
That was the initial thought, but the SOFIA data suggested something more subtle and actually more profound. It wasn't necessarily about where the comet came from, but how the water was being released when we observed it.
How it was released. What does that mean?
Well, SOFIA's instruments could distinguish between water vapor coming directly off the comet's nucleus surface as ice sublimates versus water vapor coming from icy grains being ejected out into the coma, the atmosphere around the comet. And they found a correlation. The measured DH ratio seemed to depend on the mix of these two sources. Specifically, water released from those ejected ice grains seemed to have a lower, more Earth-like DH ratio.
So you're saying the comet's internal composition might be more uniform, more Earth-like than we thought. And what we measure depends on how much of that internal stuff gets released.
That's the implication. If the water locked deep inside the comet, preserved in those grains, is actually closer to Earth's ratio, then potentially many more comets could have contributed to Earth's water supply. Our earlier measurements might have been skewed by only sampling the surface layers or specific release mechanisms.
That changes everything. It wasn't the comets themselves necessarily, but how we were measuring them.
It seems that way. It suggests the water composition might be more universal, and the high DH ratios in some Oort cloud comets might be related to processing on their surfaces over billions of years, or how they outgas, rather than reflecting their bulk pristine composition.
Okay, so we've swung back. Asteroids are still players, but comets, particularly Jupiter family ones, are definitely back in the game as potential water carriers. And all this water, whether from asteroids or comets, seems to trace back to that ancient pre-solar ice.
That's the unifying theme. Comets, in particular, are considered time capsules. They're arguably the most primitive objects in the solar system, preserving material from its earliest days. Even with 67P, despite the overall DH mismatch for water, the Rosetta mission found that many other volatile molecules, things like nitrogen, carbon monoxide, organics, showed strong similarities to molecules found in cold interstellar clouds. The building blocks were clearly ancient.
Right, and this loops back again to the deuterium measurements, but maybe looking even closer, like at the DO specifically.
Precisely. Remember the DO detection in V883 Orionis? That specific molecule, heavy water, also provides clues when we look closely at comets like 67P. Researchers analyzed the relative amounts of singly deuterated water, HDO, versus doubly deuterated water, DO, in 67P. Even though the overall DH, mostly measured via HDO, was high, the ratio of DO-HDO compared to HDO was found to be extremely high, about 17 times what you'd expect if the water had been thoroughly mixed and processed, say, in the hot solar nebula.
What does that ratio tell us?
It's another strong chemical signature. That highly non-equilibrated ratio between the different deuterated forms is characteristic of water ice that formed in the extremely cold interstellar medium and has remained frozen and largely unprocessed ever since. It tells us the water molecules themselves weren't broken apart and reformed in the heat near the young sun. They survived the journey intact.
So even in a comet with a high overall DH ratio, like 67P, the internal relationship between its water types screams ancient interstellar ice.
Exactly. It's further confirmation that the fundamental water molecule is an inheritance delivered via asteroids and comets, but originating in that pre-solar cloud.
Okay, let's try and synthesize this then. We have the V883 Orionis data showing DO forming before the star. We have carbonaceous chondrites from the asteroid belt matching Earth's DH. We have Jupiter family comets also matching Earth's DH. And we have the internal chemistry of even mismatched comets, pointing to unprocessed ancient ice. What's the big picture now?
The big picture is definitely one of mixed delivery. It's likely not just asteroids or just comets. Earth probably received its water from multiple sources, arriving late in its formation.
A cocktail, basically.
A cosmic cocktail, yes. Primarily hydrated asteroids or planetary embryos scattered inwards from the outer belt, carrying that chondritic water signature, but likely also a significant contribution from comets, especially those originating in the Jupiter family region, delivering their own payload of ancient ice.
But the crucial point is the origin of the ingredient, the water itself.
That's the key takeaway. Regardless of the delivery truck, asteroid, or comet, the cargo, the water molecules were forged in the unimaginable cold of interstellar space, long before the sun even switched on. That heritage seems undeniable now.
And this has huge implications for life elsewhere, doesn't it? The V83 Orion study mentioned something interesting about organics versus water.
Yes, that was fascinating. They found that while the water ice in the disk seemed pristine, untouched, some of the complex organic molecules seemed, well, slightly altered, perhaps by heat or radiation closer to the star.
So the water survives better than some complex organics.
It seems so. Water is remarkably robust, and if this interstellar inheritance of water is common, if most forming planetary systems receive this ancient, pristine water ice, it means planets forming in the habitable zones might get a ready-made supply of the most crucial ingredient for life as we know it.
They start out with the solvent, the foundation for a biosphere, already delivered.
Exactly. It suggests the potential for life might be seeded very early in a planet's history, built upon this cosmic water heritage.
So, that completes our deep dive for today. We've journeyed back billions of years to find that the water in your glass likely started its existence in the cold, dark vacuum of interstellar space, even before our sun was born. And we've seen the delivery story evolve from a simple asteroids did it to a more complex picture involving both asteroids and comets, all traced by that subtle DH fingerprint.
Absolutely. And it leaves us with a rather provocative thought, doesn't it? We know some other volatile molecules found in comets, like nitrogen gas or carbon monoxide, seem more fragile. Their abundances change over time. They don't seem quite as pristine as the water.
Right.
But if water, which is so fundamental, can survive that entire incredible journey from the interstellar cloud through star and planet formation all the way to us, completely intact,
Yeah.
well, it makes you wonder, what other simple, essential molecular building blocks for life might also be making that same journey, preserved and delivered, just waiting for the right conditions across the galaxy?
Something to ponder indeed. That ancient history swirling in every drop. Thanks for joining us.